Hello, my name is Roberto Lopez-Anido. I'm professor with the Department of Civil and Environmental Engineering at the University of Maine, and also I conduct research at the Advanced Structures and Composite Center. The title of my presentation today is 3D printed formwork for railroad bridge precast concrete ballast retainers. I would like to start with the need for having 3D printed formwork. What is the problem? Manufacturing complex formwork is a labor-intensive task that requires skilled manpower. There is a need to develop durable and cost-effective forms, as well as tooling for precast concrete parts used in transportation projects. What is the solution that we are proposing today? Use additively manufactured, we also call it 3D printed thermoplastic composite, that's the material, formworks for casting precast concrete structures. But to do this, we need to work in a large scale in such a way that we can manufacture concrete parts with fairly complex geometry. Complex geometry is really where the opportunity stands for the use of 3D printing. Based on the feedback we received from the Maine Department of Transportation, we identified a railroad bridge project to prove the concept of this technology. This is a strengthening and repair of the bridge at the Sheridan Road in Ashland, Maine. This is part of the Maine Northern Railway, Madawaska subdivision. I'm showing here a picture with a span to the approach for the main deck truss that goes over the Aroostook River. In the design proposed by Maine DOT for the strengthening of this bridge, precast concrete is used as a ballast retainer on both approaches. Each approach consists of 3 pieces, precast pieces. The dimensions are shown here. The width is 20 feet, the height 6.5 feet, and the length 4 feet. So when we add the 3, we'll have the 12 feet long approach. This is a part that has some level of complexity. Why? We have a slab with a 2% cross slope. We also have the taper sides. So making formwork for this part is challenging. And here comes the proposed solution. Use 3D printing in such a way that we can manufacture a form using this large format 3D printing technology to cast each of the precast concrete pieces. To be able to do this, we need an efficient design. So we work on different designs that allow us to reduce material usage for the 3D printed form, as well as lower the 3D printing time. That is the way really to reduce the cost. And we came up with a cellular design. You can see an illustration here in the figure. It is similar in a cross-section to what we can call a truss design. So you can see there the overall shape that the form will have to be able to cast these individual precast concrete pieces. We had to select the right material for the form, and our criteria was based on prior experience. We selected carbon fiber reinforced ABS. ABS is a typical polymer used in 3D printing. The reinforcement with carbon fibers is about 20% by weight. These are short carbon fibers, but they add the required strength and the stiffness that we need for this part. This material has been used before for architectural precast applications. But what is novel here in this project is the use in fairly large structural applications for transportation infrastructure. To give you an idea, the total weight of material used for this form was about 6,300 pounds. We work on the design of the part. We have several iterations with our collaborators at Maine DOT and also the producer, American Concrete, with their plant in Veazie that is fairly close to the university campus. So we had an opportunity to go several times and discuss this in person with their project manager there. And we were able to come up with the loads that the form will see during casting fresh concrete. In that way, we were able to do structural analysis. We use finite element to properly capture the way the material will be stressed and deformed and the fresh concrete loads during casting. And in that way, come up with the required thickness for the walls and the required geometry for that cellular structure that we have seen before. Once we agreed on the design, it was time of making the part. And we see here an illustration on the right of large format 3D printing. We make the part by layers. We build layer after layer over the bed, where we control a number of parameters like the speed at which the head is applying the material, if the temperature, we can control the temperature of the bed, for example, and in that way, build the material with minimum amount of distortion and with a shape that is very close to the final shape of the part. Of course, we couldn't make the entire form at once, so we had to break it into pieces. In this case, we designed 10 different pieces, and we will need to assemble them. And they will have also to be disassembled when the concrete part is removed, when we're stripping the concrete and reusing the form. Therefore, we had to design the pieces to be bolted together. We carried out the design of each piece in such a way that we have a continuous tool path during 3D printing. This is really important because if this doesn't happen, we'll have kind of stops and starts again that create weak points, potential for stress concentrations. So the design of the tool path is really a very important component in the structural design of the part. The parts were designed in such a way that we have a layer time, that's the total time to complete each layer, that is about 5 minutes. So we look at what are the maximum dimensions that we can attain within that layer time. The extrusion rate of the machine that was used, the extruder that was connected to the 3D printer, was about 23 kilograms per hour. There is an image here showing the parts being printing, and you can see one part standing and the other one, we're building the required height, and you can see the head there of the extruder machine. This machine is called Big Area Additive Manufacturing, or BAM, and it's one of the large format polymer extrusion-based 3D printers available. There is one at the University of Maine. The one we use in this project actually was placed at another facility. At that time, we didn't have our machine fully operational. Here we have an illustration showing the as-printed parts. On the right, you can see two of the pieces with the cellular structure. The surface, because we're building by layers, we have a roughness that needs to be machined to get the proper surface quality for casting concrete. To give you an idea about the times required to make the parts, and these parts were manufactured at a company, Additive Engineering Solutions, in Akron, Ohio, that again has a printer that is kind of a twin printer of the one we have in our lab at university. For printing, the total time was 96 hours for the entire 10 pieces. Remember, I mentioned about 6,300 pounds of material were applied. But then we had to surface or machine the surfaces that are in contact with concrete with a CNC machine. That took about 140 hours. So these are items that have to be considered when we look at the cost of making the forms. Finally, the pieces were placed on a flatbed, on a track, and were shipped all together to the producer in Veazie, Maine. So we're going to move now to the precast concrete plant. So the parts get at the plant, and they are assembled to get the full formwork. Again, this is an American Concrete Industries plant. You can see in the images the surfaces that have been CNC machined. These are the surfaces that are in contact with concrete. And again, you can see the cellular structure of the formwork that will give it the required strength and stiffness. Here, the parts are assembled. They are bolted together. And we can see in the plant, even on the image of the right, on the right, we see some of the rebar reinforcement already placed there. It was important in the design to locate the bolt holes in a way that can be accessible and then can facilitate the assembly and disassembly of the part. We have done quite a lot of work on this, again, working closely with the producer, and got feedback on ways that we can even do it better for future formwork projects. These are some illustrations of the formwork of the plant, different stages of the fabrication process. We're looking here at the rebar placement. The feedback we got from the fabricator was working with this material really didn't have any significant issues. We got some good lessons learned that we plan to apply in future projects to, again, come up with a more practical formwork. But overall, it worked really well and very similar to other conventional materials they have used for formwork in terms of their experience and the work they require for casting concrete. So here we are going now to the concrete pouring stage at the plant, and this is where we have the fresh concrete producing pressure on the forms. The material, if the concrete was vibrated, traditional way of making these parts. Again, they were not required any special adjustments because we're using these 3D printed forms. The parts are being finished to get the required surface there. And we can see here a number of operators trying to complete one of the pieces. And remember, there were 6 of these pieces that were made with the same form. So the form was, again, reused a number of times. And that was a good measure also of the durability of the material. I mean, at least we know 6 times works really well. Some details so you can appreciate how the pieces were bolted, connected together. And again, the design was intended to facilitate the reuse of the form, the number of times required for all the pieces for the project. And in that case, we, as I mentioned before, 6 pieces total to form the 2 approaches for the ballast retainers for the bridge project in Sheridan. So we have here some of the pictures of the final precast concrete pieces. On the left, 1 piece inside the plant, and then place the 6 pieces together at the yard, waiting to be shipped to the bridge side. And I put there in detail on the marking on the parts, just to remember. You can look at the date there. The parts were casted May 2022, and the bridge project number where they're going to be shipped. So now it's time to move to the bridge side and see what we learned at the bridge side, now with the concrete pieces that were made with this technology. So we are here at Sheridan Road Railroad Bridge in Ashland, Maine, and we have the parts being placed at one of the approaches. 2 parts are placed on the figure on the right, 2 pieces. Here, one of the approaches with the 3 pieces of precast concrete and the operation for filling with ballast. Again, the quality of the parts, it met all the requirements. The surfaces were as expected. No issues with any deformations of the formwork that would alter or change the geometry of the precast concrete plant. Everything really went well. We have an overhead view how the bridge looked like after the approaches were completed. And now it's time to think a little bit about what are the conclusions, what have we learned, what can we do next? And well, again, the material can be reused 6 times at least. We'd like to know actually how many more times we can use it. I mean, look at the longevity of a form in a project. But for this type of projects, again, it will depend on the number of uses at the precast concrete plant. Overall, the project was successful. The implementation went really well. I mean, again, the work at the producer, the work at the site, it was done as planned. One important observation is, well, what happens now with this material? And that is important because we want to be able to reuse the material. So it's important to know that this carbon fiber reinforced material, carbon fiber ABS, can become an asset, meaning it can be recycled. So along those lines, we started a recycling study. We're doing this at a smaller scale with the intent to be able to recycle those 6,300 pounds of material that were used for this project. So again, the intent is how we can shred the material and repelletize it, meaning come up again with the feedstock that we need for the extrusion process in the 3D printing machines and produce another part. Something we are learning in this study is that there are some changes that happen to the material when you recycle it. It changes that can affect the what we call fiber length distribution for the carbon fibers, or changes that can affect the molecular weight of the polymer. So we are trying to characterize that and see what is the effect on mechanical properties like strength and stiffness to look at the feasibility of recycling this material. This goes also together with the cost, the energy cost of recycling. Again, this is where we're focusing right now, where we see the opportunity, come up with a good prediction in terms of the number of uses the material can have and what can be the cost advantages over the life cycle. I have here a brief list on lessons learned to share with everyone. It's very important in this type of application, the ability to repeat assembly and disassembly. It's also an opportunity to continue to refine the design based on what we have learned in the project. One of the aspects that is very important are connections and the access to the bolts. I mean, that's where we'd like really to do some fine-tuning in the next project we work on. It is important also to stiffen the top of the formwork parts to minimize any deformations of the forms. And that can allow us also to reduce the weight of the formwork. I mean, try to come up with a design that is even further optimized. I mean, based on the cellular type of configuration that I show you, that truss structure, but with stiffened top edges. The goal, again, is to produce a cost-effective formwork. I mean, we look at some of the cost items. I would emphasize the cost of material, the printing time, and the tooling time. I mean, those are, or the CNC machining time. Those are the 3 big cost items. And any design that can allow us to minimize them will result in a more cost-effective product. And then this has to be, again, added to the possibility of recycling the material. I mean, what can be the benefit of having a material that can be reused many times for different projects? What we want to do here is make 3D printed formwork practical for construction applications. So the intent of this project was not just to look at material science and manufacturing aspects, but also to look at practicality. I mean, what type of feedback we were getting from the producers, from design engineers, and how we can, again, have this technology go into the transportation infrastructure market. I mean, for projects that can go from railroad bridges like the one I showed to highway bridges and others. I want to share who are the great collaborators we have in this project. And I would like to mention Dr. Sunil Bandali, postdoctoral research associate with the Advanced Structures and Composite Center, who was responsible for the structural analysis and design and a very important part of my research team. Joe Stilwell was the fabrication engineer for Maine DOT, was really a champion for our project and provided very important feedback on the implementation at the bridge site. O.P. McDonald, the vice president and general manager of American Concrete Industries in Veazie, worked together with us on refining the design of the formwork, again, to make it practical and providing important feedback on the experience they learned at the plant. And finally, and not least, I want to acknowledge my graduate students. You can see here some two graduate students, the two on the left in the photo, who work on the project and help in many ways, and that they are conducting two important studies, one on durability and one on recycling of these materials. I want to thank, in particular, the Transportation Infrastructure Durability Center at the University of Maine, who has provided the funding and support for this work. And at this time, thank you for your attention and welcome any questions at the end of these sessions.